All right, we are in section 12.3. This lesson is about what's called the dot product. So our outcomes are we're going to define the dot product and discuss the properties and the geometric meaning and apply them to the direction angles, projections, and what's called work. So a couple of things that we need to talk about real quick is that the dot product, this is a nice one because it's a crossover. This one is actually used heavily in linear algebra. There's another product that we're going to do, which will actually be in our next section, which is called the cross product. These are two different types of multiplications when it involves vectors. So this is really the first, or we're just going to say one of, because it depends on what order you learn them in, but one of two vector multiplications. And there are actually several more when you learn about linear algebra. There's different ways you can do things when it comes to vectors, specifically vector spaces, but that's not this class, it's a different class. So the way we're going to represent these is with familiar notations. And it's just something that obviously now at this level you're going to have to make sure you don't get confused with the way we used to do things back in like elementary school. But the first one is, now when you see this, that actually represents a dot product. It's also a multiplication symbol, but it represents a dot product. And then the other one, when we get to it on the next lesson, is called a cross product, and that looks like that, just looking like an X. So again, don't get confused, but that is the notation. So the dot represents the dot product, the X will represent the cross product. All right, this is actually one of my favorite ones because frankly, it's very easy to do. The meaning behind it is definitely more important because the actual process of doing a dot product, very, very simple. If you have a vector, and we're going to say that both of our vectors A and B here are three-dimensional vectors, they've got three components, then the dot product, or vector A dot vector B, is given by this formula. It's A1B1 plus A2B2 plus A3B3. Or in other words, you just take the first component of each one, multiply them, take the second component, multiply them, take the third component, multiply them, and then add all the results together. And if you're going to do that, considering that all these components here are going to be numerical, if I take two numbers and multiply them, two more, multiply them, two more, multiply them, add them all up, we get a scalar. We just get a number out of this. So the fact that the dot product gives you a scalar is very important to know. So let's actually just go ahead and try one. Again, this is very simple to do. Our first example is we're going to take vector A, 2, 3, negative 1, and dot it with vector B, 5, 0, 2. So according to the dot product, A dot B is going to be 2 times 5 plus 3 times 0 plus negative 1 times 2. And that should actually look like a times 2. It kind of looks like a minus 2 times 2. So we get 10 plus 0 minus 2, or the dot product of those two vectors is 8. Again, very, very easy to do. Of course, the whole idea is what does all of it mean? We're going to get to all that. We can dot two vectors that are in IJK form. Remember that the numbers out in front of the I, J, and K are really just your vectors. So we could rewrite vector A in standard vector form of 2, negative 3, 1. And vector B we could write in vector form as 4, 5, negative 3, and now we can dot A and B very easily. You don't have to do that step that I just did right there, by the way, if you know how to do this without it. Just showing you that sometimes it's easier to see it in that notation, but it doesn't matter. So here we're going to get 2 times 4, which is 8. Negative 3 times 5 is negative 15, and 1 times 3 is negative 3. So we get the dot product is 8 minus 15 is negative 7, minus 3 is negative 10. Again, not very difficult to do. So we've obviously obtained a scalar, which is what we said we were going to, but what does it actually mean? Well, first of all, we're going to look at some properties, and then we'll actually get into the meaning of this.